Hello and welcome. This is Deep Linux. This will be the last video in the series about Heap, and you will have a full picture of what the heap does and how is it structured and all the different bins. Okay, so in this video, I'll be talking about the per thread cache. The per thread cache, or as short we call it Tcache, is a feature introduced in glibc 2.26. So it's relatively recent, if you may. And what it does is that it adds a little bit of more performance gain when it comes to multi-threaded applications using the heap. So how does per-thread cache work? Well, if you remember, I mentioned that whenever we have multiple threads, so let's say we have thread 1, thread 2, thread 3, uh, all of these would normally contend for the main arena. So let's say we have a main arena, and they would contend for this. And the way that they would contend for this is they have to acquire a lock, which is called the mutex lock. So main arena mutex. But because we don't want this to happen, we instantiate multiple heaps and we call them arenas. So arena 1, there's going to be another arena 2, and then we'll make T2 only work on arena 1. T3 only work on arena 2. Well, the thing is, we can't really force them on any particular arena because threads actually share data structures and memory between each other. So if, let's say, you allocate a variable x here and you want to refer to this variable in this thread here, sorry, if T2 wants to refer to this x, so in that case T3 and T2 would use the same variable, meaning that you're not really removing the actual critical section. You're not really removing the race condition. However, you would be removing the race condition when it comes to allocation and freeing X. So as a good practice, it's good that whichever threads allocate a particular memory, the same thread frees it. Because that means that, every thread would be confined to only one mutex lock, which is always going to be, available for that thread. Every thread is going to be confined to an arena. But if it happens that a thread allocates memory and then another thread passes the pointer to another thread, which would then free the memory, then you'll have two threads on the same arena. So this is something that, have in mind if you're coding. Sometimes maybe you can optimize for that. So even though we have multiple arenas, we're still gonna end up in situations like that. But anyways, arenas are there to alleviate or reduce the amount of thread contention on heap. However, even though we may potentially have a one-to-one relationship between these arenas and threads, the problem is that we still have to get the lock, right? Because we can't be sure that there is no guarantee that another thread here is not going to access this one. So you still have to get the lock whenever you want to access any of these. So this is a must. However, we hope that most of the time when we want to get the lock is free. But anyways, even if the lock is free, there is some overhead in acquiring the lock. So if you want to, acquire a mutex, which is unlocked, right, which is locked, you're definitely going to have to block. The overhead is high. But even if the mutex is unlocked, meaning available, free, just acquiring it and proceeding with the execution, that in and of itself has some significant amount of instructions to be executed. And because malloc and free are actually one of the hot paths in um, program execution, we want them to be as quick as possible. So the idea is have a way for threads to operate on heap in a lockless way. Or let's say, in a sense, have a lockless heap. Now, we can't really have a lockless heap, but we can somehow create a cache of free blocks of memory that, if required, would be provided to that thread in a lockless manner. And this is what we call the per thread cache, or Tcache. Because this is a cache which is part of the thread specific memory of a particular thread. Okay, let's look at the code a little bit to understand this better. So you see all the part related to Tcache, it's enclosed in if use Tcache, which is true since glibc 226. Let's see what we have here. So again, Tcache has its own bin. So Tcache is actually, oh, by the way, I have a spelling error here. Just realized. Tcache. Sorry for that. Yeah. So again, Tcache is basically organized as a set of bins. So we have these bins here, right? And we have again a number of so there is basically a concept of what sizes go into those bins and how many of those blocks go into each bin, just like the other bins that we had. Okay, so Tcache is essentially similar to fastbin, meaning that whenever you free something, first you send it to the Tcache, and you don't mark it as a free. So the p bit is the prev in use bit basically is still set, meaning that the block of memory looks like it's allocated, right? Just like it was for fast bins. So you're gonna free it. You're not gonna change it at all. You're gonna it's gonna look like it's still active and allocated. You're gonna first put it on the Tcache, then after a certain amount of time or certain condition, it will end up in the max bin, in the fast bin. Then after a certain amount of time, it will be coalesced and it will be sent to the unsorted bin, and then the small bin and the large bin. So the way it works is, if I want to give you a diagram of that, is that whenever we have free, okay, let's say a block is freed. Free block. That block is first gonna end up in the Tcache. And Tcache is obviously a list. It's basically a linked list, but I'm just going to show it like this. If it doesn't fit into the Tcache, let's say the Tcache is full, or the size is above the amount that the Tcache can accept, then it will be sent to the fast bin. So here we have the fast bin. And we already talked about fastbin in another video. Okay, so fastbin is not per thread, is not per any particular thread. It's basically bound to an arena. This one is bound to a thread. So for instance, if there are 5 threads on the same arena, they are going to have the same fastbin, but they're going to have different Tcaches. And that's very important. And then it's going to end up in the unsorted bin. And then the conditions with which these are triggered are kind of complicated, so I don't really want to get into that. And then this is going to be distributed into either the small bins a set of small bins, um, which were 62 small bins up to 1024 minus 16, which is going to be 1008 bytes. To yeah, that's going to be bytes, and then the large bins. Okay, so these will be the large bins, and we already talked about this. So this is the life cycle of a free bin. And if you do a malloc, the malloc is first going to go look here. If there is something there, it's going to return it. And by the way, the p bit is going to be 1 here, and it's going to be 1 for the fast bin. So it's going to look like these are active, basically. These are going to be active blocks. They're not going to show up as free blocks. The other ones will show up as free. So malloc is first going to go look into Tcache of this particular thread, right? Then if it finds it, it's going to return it. If not, it's going to look into the fast bin. So first and then second fast bin. Then the unsorted bin, and then depending on the size, it's going to go look in one of the small bins or the large bins, and then eventually return it. Or if not, it's going to get it from the top chunk. If not, it's going to extend the heap. So this would be 5, and then this would be 6. And if not, then it will return null. Basically, we ran out of memory. So this is how malloc and free work. Now you have the entire picture of all the bins, all the cache, and everything. And just realize that there could be more than free memory stored in terms of bins than you have actually in use allocated memory. And this is a very interesting fact about glibc and any other libc or any other heap, that you could have a lot of memory used or actually claimed by the application, taken away from the kernel, and yet maybe 50% of that, or I've seen even cases where 80% of that is just free, sitting there in terms of cache. And we call this we call this heap bloating. And this will be a subject of a future video if I have the time. And we will see some very interesting issues. But okay, this being said, now let's drill down into Tcache and see where it's stored and how it looks like. And okay. Okay, so one of the important structs here is the Tcache pthread struct, and which basically there will be one of these per thread, which contains the number of basically number of available free blocks inside each one of these bins. So you will have a Tcache max bins, and then each one would include some number of blocks. And the entries is basically the actual um, entries for that the actual blocks there. And we have allocated a Tcache of this type and assigned it to null at the beginning. And what we do is that initially, when we do the first malloc, what happens is that you allocate this and initialize it, right? And pay attention to this thread keyword here. This means that allocate this as part of the thread specific or thread local storage. So this is going to be for this thread only. That means that this memory is not like, it tells the compiler that allocate this memory from a space which would not be shared by other threads, meaning that if there is only one arena and 10 threads, they will contend for the arenas, but for those blocks of memory that are freed and end up in the Tcache, every one of them will have its own Tcache, so they will not contend for the Tcache, which is very good. So this is lockless operation as far as the Tcache is concerned. Okay, what else do we have here? That's the shutdown. That's the Tcache init, right? So this is the initialization. You can see that um, there's gonna be, yeah, there you go. Uh, see this bytes here? That's the size of that struct. What's happening here is that you're getting the pointer to the arena. So for a particular arena, right, you're doing a malloc, and this is the internal malloc. Basically, this is like it's something internal in glibc. You're doing this much malloc, right? It's an internal malloc again, and you're actually, basically creating your Tcache as the first block in this particular heap. That's what's happening here. Okay, let's just see this. I'm gonna run actually sudo gdb, because I'm gonna attach, and I'm gonna say, well, I'm gonna run the benchmark here. Sorry. Yeah, I'm gonna run my benchmark, but I'm not gonna limit the arenas, nor am I gonna limit the Tcache. So I'm just gonna run it with the default options. So this is here, and then I'm gonna say PID of bench this 68522, and then I'm gonna say attach to this. Okay, now it's attached. Let's look at the malloc parameters. Well, you can see that I have a Tcache count of 7, meaning that there will be so here we have 64 bins. First off, let's look at this. We have 64 bins, and the max bytes stored is 1032. That's the maximum size block that gets stored in the Tcache. And in each bin out of these, so for every one of these 64 bins, each of them can contain a maximum of 7 free blocks. Okay, so 7 free blocks times 64. That's how many blocks we're going to hold in total in the Tcache. Okay, now how are the sizes distributed? Let's take a look at that. Okay, So here in the malloc.c code is where we see the explanation and the code, the implementation of the number of bins and so on and so forth. Uh, we have 64 entries here. This comes from here, Tcache max bins, which can be reduced by the glibc tunables. And max Tcache size, here it's explained here that um, the bins, however many we have, will be sized like this. So for instance, bin ID 0, bin index 0, will include bytes 0 to 24 for 64-bit systems. So if I malloc from 0 to 24 bytes, then it's going to end up in Tcache 0. And this is actually the data part. So it's going to, you know, the actual size is going to be a little bit more than this. Blocks from 25 to 40, which is 16 bytes more than this other bin, is going to end up in bin 1. Bin 2 will be up to 56. Bin 3 is going to be, where's my calculator? So bin 2, 56, 56 plus 16, that's bin 3, 4, 5, 6, 7. Okay, so bin 7 is going to hold everything up to like 120 up to 136 bytes. So this is going to be bin 7 and so on and so forth. Now, every bin contains at most 7 chunks, and this can be again changed. And this was the glibc tunable that I was using here as basically this is the glibc tunable responsible for this. glibc malloc tcache count is 0. This is how I disabled it, because I told it that these 64 bins that you have, make them occupy 0 free chunks. That's kind of essentially disabling tcache. Okay. Now you can change this if you want. You would be using more memory, but then you'll have more free blocks of memory that you can recycle lock free, which is very important. And so let's say if we have 64 entries, okay, we have 64 entries and we start from 24. So 24 plus 63 times 16, because everyone is larger by 16 bytes from the previous one. We end up the last one holding blocks up to 1032 bytes. Okay, and this is the value that you got here, 1032, because you had 64 bins, right? And they started from 24 and then 16 bytes increments going up. So that's how you end up with 1032. Okay, it's very similar to the fast bins, but these are lockless and specific to a certain thread. So what that means is that if a block of memory ends up in a Tcache of a certain thread, no other thread can use that. Okay, now let's look at how these look like. So if you remember, we had this Tcache variable somewhere that was null, and then it would be allocated, right? Right now, if I say info thread, I'm on thread 1. I can go to thread 2 by saying thread 2, right? Anyways, I'm going to print Tcache. That's the struct. And what I'm going to do is I'm going to print the contents, count 0. It's all empty. Okay, now I'm going to change my thread. So I'm going to say thread 2. Go to thread 2, which is this one. Okay, Now it's changed to that. If I say, yeah, okay, so that's what it is. Okay, so this is my malloc parameters and whatnot, and you already know this. Now I could go and say Tcache. Now pay attention. Here, when I said print Tcache, this was the address. Here in this other thread, this is the address. So you see, it's different. The Tcache has a different value. So these different threads, different Tcache. So let's see what's inside of it. Okay, so these are the counts. So it's actually telling me that bin 1 or 0, however you want to number them, contains 4 free blocks, 6 free blocks, and then this is basically size 0 to 24, size 25 to 40 from here. There you go. Size 41 to 56, and so on and so forth. Okay, and these will be the entries for these guys. So basically, this is the first block of bin 1, first block of bin 6. So let's just print them and see what we get. Actually, what I'm going to do is I'm just going to dump the whole memory for this Tcache here. Dump the memory. There you go. So you see these, this is kind of the linked list here. This is a linked list, just like the other linked list that we had in fastbin and whatnot. So this will point to a free block. Okay. So we're gonna say print again star Tcache, and then this is it. And I'm gonna look at entry 0. Entry 0, right? Which there's a next and a key. And the way Tcache works is that the key points always to the Tcache itself. So if I say Tcache, you'll see that this is the same. So basically, we're linking back every block of memory in the allocated on the Tcache to the Tcache that it belongs to. If you look at this part of the code, where it's about putting a free block into Tcache, and this is called when you do free. So if you go, let's say, and yeah, int free. Actually here, int free, and the function free. This is when you call free libc free, internally it calls int free, and then as you go down somewhere here, it will say if my Tcache count is not exhausted, then put this on the proper index in the proper bin. And so I'm looking at Tcache puts to see how this happens, and I'm creating a Tcache entry, okay, so which is one of these, and I'm assigning the entry to, I'm actually assigning the pointer to the actual memory, not the metadata, and putting that into that Tcache entry. So Tcache, okay, the pointer in the Tcache is pointing to the actual pointer that's returned to the user, not to the 8 bytes before, which is the beginning of the metadata, right? Let's just have that in mind. How do I know? Because it says chunk, then go from chunk to mem, which is going to go from the metadata to the actual pointer, data pointer, and then typecast as a Tcache entry and return this as a Tcache entry, and then set the key to the pointer to Tcache. This is what we just saw here. Key points back to the Tcache itself. And then here you kind of insert it into the linked list, right? So if I want to know what block of memory is at this point in the Tcache, I should say, okay, Tcache entry 0, right? And then now I want you to var star deduct 16 bytes, go back 16 bytes. Actually, sorry, go forward 16 bytes. No, sorry. This is the actual data pointer. So go back 16 bytes. And this will be the actual data. The actual metadata, sorry, getting confused. And then print this. So what we're going to do is, yeah, that's it. So we're going to treat this not as a char star, as a chunk. There we go. So this is the first thing that's on the Tcache for this thread in entry 0, right? That's the first block. Previous block is 48. This one is 37 bytes. And this is the forward pointer and the backward pointer. So it's kind of, this is the linked list, right? And this other part we can just neglect. And I can go and actually do entries next, and this will be the next one. Okay, so if I do a next here, this is going to be the next block. The backward pointer is actually not the backward pointer here because we only have 4 single linked list. The backward pointer is going to be this key because they're doing these repositioning. So, and this is going to be the size, the prev size. This is going to be the chunk size. This is going to be the next pointer in the linked list, and this is going to be the key, which is going to always point to my this particular Tcache, which has the address as, where did it go? Here. This is it. This is my Tcache. Yeah, this guy here. Okay. Now you can see that all of these have the same size, 37 bytes, 37, because they belong in the same Tcache, right? Now note that these are not consecutive. These are not adjacent in the memory, right? They are from different addresses, but they're put in a linked list. So this, so don't expect like that the prev size. So for instance, don't expect the prev size here to point to actually this other one. No, this is going to point to the block before it. So we're actually having these blocks in the memory, right? But then we're running a linked list through them. We're stringing them together through a linked list, just like how we did with fast bin and small bin, and same goes with Tcache. Tcache is simply a linked list. We are not really putting the blocks of memory in a different list. We're just, the blocks of memory are there, accessible by all the threads. We're just putting a linked list of a certain number of these blocks in a certain space only dedicated to a particular thread, right? So that thread knows that if it goes over that list, nobody else is going to be using them. Okay, why? Because those blocks are in use. Those blocks are not free. So so nobody else is going to actually go and use them. No, all the other threads are going to skip it, right? But this guy, because it's in its Tcache, it's going to be able to use it. Now let's look at one of these. So this guy here, I'm just going to dump this, right? And I did it here. The first Tcache block on the first bin. Here it is. 25 is the size, and the previous one has the p-bit as set. The next one, sorry, the next block has previous bin, previous in use bit set, meaning that this block is considered active by Heap. So again, just like in fast bins, Tcache and fast bin, whatever ends up there is not truly free, right? The p-bit is still set. I think it's enough. It's just getting more and more complicated as we go. I mean, the best way to go about these things is not to do eye inspection, but maybe to have these macros that you write, and then they will go through the Tcache for you and make sure that the Tcache is fine and sound. Let's do another thread. I mean, you can do this all day, right? And then p Tcache. Okay, very. This is another one. And it's different from this one. This is F00 something, F08, F00 something. This is F08, D4 something something. Okay, so you see, it's a different thing. Okay, now what I'm gonna do next is I'm gonna see what's the performance impact of having Tcache on or off. I'm gonna have this glibc tunables with Tcache set to 0, and I'm gonna have all the arenas and everything. So I'm not gonna be taking any futexes. It's really, I'm not gonna be basically locking or blocking on a futex, because I have so many arenas that all the threads will get their own arena. So it's very, very unlikely that 2 threads would contend. The threads are going to have to acquire the lock. But that acquiring is always going to be successful. So let's see what's the difference between successfully acquiring a lock and not needing to acquire a lock at all. Meaning operating lockless using Tcache. So now here Tcache is disabled. See how many cycles we get per malloc free. You see that we have 121 CPU cycles per allocation thread. Now, what I'm going to do is I'm going to enable Tcache, the default 7 blocks per bin and 64 bins. And let's see what we get here. What we're expecting is we're expecting to see less CPU cycles per allocation and free. Wow, it's a lot of improvement. So going from 121 CPU cycles to 71 CPU cycles. That's a little bit shy of 50% improvement in terms of the CPU cycles and speed. So you see that having this Tcache allows us to have a lockless heap to a certain point, up to a certain number of blocks, up to a certain size, but it goes a long way in terms of performance. So we've seen so many different performance improvements done to malloc, to basically heap. We've seen the fast bins and the effect of them. We've seen the astronomical effect of the arenas for multi-threaded applications that would reduce the number of calls to the futex, which is basically where you would actually have to get the lock and hold the lock, right? We also saw the effect of having a per-thread cache, which removes the requirement to hold the lock in some cases, actually, and allows for lockless operation. So all of these performance improvements together is what you get when you use glibc, right? And as you've probably realized, it's a very complicated beast, and troubleshooting issues with Heap is really, really challenging, just because of this amount of complexity that it has inherently. I hope you've enjoyed this video. I hope the series has caught your attention, and I hope I can put up with this and add more interesting videos about Heap. In particular, I'm thinking about a video for troubleshooting memory leaks, for talking about cache bloating, or the glibc heap bloating issue. what memory is actually considered free, what memory is actually not considered free, and so on and so forth. So stay tuned for more videos about Heap. And thank you for following this channel. Please don't forget to subscribe and hit the like button if you enjoyed it. And I would also welcome your valuable comments. Thank you very much.